Okay, so here is the lecture number 9, right? Okay. So in advanced quantum mechanics, right? Okay, so I believe last time we derived the topic. Let me put it out here. What's that? I'm not sure last time what kind of elevation to use, but anyway, it's going to be more or less the same. So here is the density. Here is action. Right here, so we have this kind of complicated, right? And so here, well, on this bit, actually, okay, infinity. So we kind of been cheating by put infinity in this kind of notation, and so but this is the beginning of that actually we get propagated in the compact form. But however, we get visible. We could not do much with it in terms of calculation, of course. That we because you don't know actually how to do this type of integration at this point, right? So this is action, this is function, this last one here. So okay, so thing is that so if you have configuration spec, like you have here and here, is 2 point. So you have a kind of infinity part where your particle, right, from initial point to the final point. Okay, and as I mentioned last time, the classical part is one of them. Suppose this is the classical part, right? Okay. So it turned out that for quadratic, Lagrangian, we can do approximation. Which is known as the semi-classical approximation. Okay. So as I explained my works last time, actually when you consider the limit, actually h bar goes to 0. The important of the classical part will get stronger and stronger, and finally you will get only one component. Because this kind of this limit, what when you do when you consider this limit, this means that you try to watch out all the quantum effects, and then this means that at this limit it turns out to be at the end the classical part will be the only part of your system. Right. Okay. So then this is kind of people to do this that way. So again, so what people need to do is that suppose we have this as a classical part, right? And we also have another part that actually very close to this classical part. And we say that the population y, the population of the part from the classical part, the Q, you change to be this one. You see? You see, it means the solution, right? This is a solution, a classical solution. Solution from the pointer from great length, and so this bit is the same that actually this is called bundle. Okay. And so the question is that why do we need to consider only the part actually close to the classical part? As I explained in the last class, actually the part actually far away from the classical part is not going to contribute to the complicated analysis approximation. And I'm not going to prove that to you, but you can, based on the textbook, where you find an ellipse from that. In that book, there is a very beautiful way to explain the reason with the mathematics step as well. Anyway, so now we have this. So for that, we can go to marking. Going to be suppose that let me see if we got a little bit more. No. This is what square. Okay, this is the quadratic in both the Q dot and the Q, right? And with this, one apply this into this Lagrangian, so you will get we have this this V1. Right. So basically, what you say is that you're going to have to do like a right. Let me do this. For an action. Okay. Yeah. Since these two things small, then we can do the expansion, right? We do the expansion. So what we get is that the first going to be this one, right? And the second term. Okay. And you also have the mix philosophy. Go like this. And there's a thing by the water. Okay. And of course, then we have all the higher order, right? But these stop here. All the higher order is go to the configuration, but we stop at the second order because since this is small, then this would be not for expansion. Okay. And in order to see that the first step is the action for the particle part, right? So with this, this action must be right. Because it is new variable. So first term will be the classical action. Okay, this is the classical action. And then it turns out that we have this. Okay. After you put this magnetic into this, all of these terms in this, and find out actually you get out. Okay. So the complicated become so you complicated now become this one. So when SC is nothing but classical action, okay, And this F is nothing but the one that actually you keep all the factors. Yeah, and maybe this. Well, the thing is that, so this is somehow called a factor. Okay. All the factors. Yeah, this is the calculation. So the thing is that in principle, what you need, so you know that actually you can compute the custom actually. You know that how to compute the custom. And then the rest of the job is to compute that figure. And but that is a bit tricky, and I really recommend you to read the book again. Five tips, right? I'm not going to show you here how to do the integration for this thing, but I'm going to give you a final result. Then I'll give you an example. And then move on. So this can be put okay. So that is the way to do it. As I mentioned, I'm going to skip it because it's going to be 10 time. But this is another, we want to have that. You can have a look again on the textbook Schumann. That is another one. Textbook actually give a very nice way to derive this big factor. Schumann, or maybe gives all my book actually. You can have a look if you want the calculation. That's anyway, that's it. So now we have a propagator in octal form. The propagator is in I would say octal form. But note this is only the quadratic dimension. The thing is that beyond this quadratic dimension, we don't have any idea how to reduce or how to do this kind of process until you get this very nice and compact form. So yeah, of this is And next, what we want to see is that what we can get from this propagator, which is actually, it should give out the same physics as we did with the Schrodinger. Right, then we start with a very simple sketch, which is actually the particle. Okay. Example. The particle. In this case, we have actually for the particle you have mass m. Is the mass m. You have x to the dot, right? And so you know that must be constant. Okay. And your x, which can be explained in terms of what?
It's, let's see,
Yeah.
yeah,
Right. It's a matter that can absorb this into the seeder, and then this can be fixed. Can be fixed by initial function. Okay. Suppose my condition, initial condition, if you has x0 here, and so x dot the we. So you use this, so you what you get. If you put 0 here, you will get, if you put t to be 0, you will get d, the x naught. And so, yeah, this should be constant. Then your c, you cannot avoid. You see, must be v, right? Then, again, your x at any time will be not, and then you say that actually this is a classical solution. Okay. Are you okay? Okay. Next, we need to compute. We need to compute the classical. So let's see. Because we gave the condition of a start from 0, and we have to integrate the vitamin T. Right. So what I do is the T, okay, and this one, okay? All right. So you can do is that you can move the constant, and then you have this, right? Which is actually we're going to have is I banding already. Okay? And then you do integrating by parts. Parts. So what you get after you to the indicator one part, what we get.
X not X.
X of X.
Yes.
X dot X right here. Minus oh, actually, this is my mistake.
Yeah.
It's not, it should be X dot X T. Here, X as well. Okay. All right, yeah. Well, okay. Yeah, right. Okay. So here what we get, or what will you get?
X B X not.
X,
B
the,
X not.
X, the X not.
It's not. It's. Yeah.
Okay, good. Right, okay. So I can do this, of course. Right. And this folding turn out to be X of the dot, X T. Right. And since you have this, your equation number, you apply your EOM, then it's going to be 0. Right. Then you left with only this, the first term. Right. Okay. Are you at this point? And so your action going to be XT X dot T, right? XT, is it? Yes. Minus X not, X not, right. And then you know actually well you can use this solution. Right. Then what you get is that it's not T is nothing but the V, right? Because it's constant, right? Velocity is constant. T is VT, X naught, right? Minus X naught, V again, right? And all the X naught. Okay, are you good here? And so you go out V. Inside the bracket, you get VT. This is going to kill each other. So, you get V squared T over 2. Oh! Okay? But the action is a functional of x, right? It's a function of x, but this is not yet a function in terms of the x, right? And we knew that v is this one, right? It is here. Then you use this v, your I put here C here as to indicate this is the customer actually. So you have n over 2, you have x3 and you have x1 t, right? T. So at the end, you get n over t. So this is your graphical action. Okay. Actually, as a function, so you can see that it's a function of x t, x right here. Okay. Now, what is the complicated look like? Oh, right. Before we go into that, we need to compute the p factor. Okay, f. Which is f. Now it's going to be function of fiber time. If you remember the formula, is that 1 over 2I h0 is it right? If I remember correctly, is it? Okay. There is a square here? No. Okay. It has. Okay, so then, what is this quantity then? What is this quantity? When you do that SC to this, you get n over t. Right? Is that right? Just n over t? Yes. No. Why not? Because if you start to do the fertility with the technology, you get to cancel this, and you get this left, and then you do the derivative again with respect to the t, xt, and all the things on. You never only n over t. Actually, you get a minus, but this is absolute. Then you can put it in t. Is that clear? Yeah. Okay, so but what is not still? Yeah. Right. You get this. Okay, this is your refactor. The power together. For the three particle, is this one. And 1, 2. Okay, this is very nice because it's already you get playing in the context. Nice because you can do things explicitly because for the P particle, the line can actually associate this P particle with in the quantum form, right? That is the reason why you can use this kind of thing to compute So,
thầy nghe
yeah,
anh thử ship why we have to consider the money why
right, right. Actually, you can go beyond the quadratic form. But once you go beyond the quadratic form, this is going to be your form. Because it is beyond the Gaussian. That is the thing. But there's no, not that we can do that, but if you write the rim of the quadratic form, then we work nicely. I think we get we get all this expression in a very nice way. But you can go beyond that, nothing against you to go beyond. You can try yourself. Of course, you can try that. Good question, actually. So, here again, complicated. And what I mean by having this complicated? This question. Can you tell me?
I have this complicated
Well, what is this complicated? What can you do with this?
what can we use it
Yeah, because this is a quantum mechanical object. Then what is telling us?
so how we can use it to solve to find position and quantum mechanics.
Define what moment and position. So, okay. Let me. Okay, let me answer actually. So in the case of three particle, one showing the equation. So you have this equation. And if you look what is the solution, what is the wave function of this?
We don't know. Oh, wave function of the vehicle.
Yes, do we know? Do we know? Okay, we don't know. Okay. Actually, the full wave function, right? Which is part and also is part, right? But we need to solve this. But with this, you can solve, right? What? So
It's a trigonometric function. Very function. A sine. Yes. Yeah.
okay, so it can now be that it's going to be some constant. And if I imagine the case, right?
Yes.
And your k, what is your k?
To find to empty or
Okay,
yes.
this is a wave vector, right? Then combine with this, so do we get right? Yeah. I'm not sure deviation. Okay. We see that it might not be H bar there. I'm not sure. Oh my God, it's not necessary. Right. And so if I pull out and then we put it in. Oh, yes. What I need is I need to be careful to make
Is perfect.
nothing wrong.
No, I think you just change the value on the.
Alright. It should be just this.
Yes, that's it.
Right. This is the bit. Okay. So, what is this? What is this solution? What is this solution? What kind of solution is this?
This.
I mean, what kind of physical? Yeah. This solution. What is this? Yeah, what is the very function? When we see this kind of solution, that actually instead of this. This is what? This is the function of. No, it's a pen wave. This is the pen wave. So you can. Okay. We have solution. Right. I mean, you get this kind of pen.
Yes.
But you can do it all plus or minus anyway. But for another, well, you can say, actually, you did that, there may be another solution with this kind of thing. I'm not sure, it might be another, like we're moving to the left and we're moving to the right. Just to have this. And so, but this is is the non-normalized function. But anyway, we know how to deal with this because you need to make it to push this wave to be a wave package, and then you goes nice, and then you get a nice wave function to represent the feedback. But for this solution, it's not have any physical meaning for this. But yeah, it's a solution. We need to figure it because it's not normalized. So we expect that we could get something like this, I think, out of that complicated question. That is the thing. Can you see that?
So just be that.
Just in how here's your forget. This is what. Oh, you can use the wall. I'm not sure why
So let's say again this.
well, here is on the showing side. You have a solution which is actually a plane wave. from this, from the Feynman technique, you also must have something similar, or yeah, the thing that we have on the showing the side. Otherwise, you're not consistent. This means that somehow in this complicated must hidden, this abstraction must be hidden in this complicated. And then we have to find a way to get it out. You know what I mean? No, it's not like what you mean. I'm not sure what you mean. What do you mean? You're saying that it's not hidden. I mean, this kind of thing cannot be kind of can be extracted from this particular. Yeah, kind of in the structure here, the it should somehow contain in this program and divide it to extract it out. Okay, I'm going to let this as homework to let you play with it, and I'm going to give you another example of our harmony oscillator. And so again, you will see that actually with another example of our harmony oscillator. Whatever you want to wish, I mean, we said that you need to you should do it, whether it be showing or refine, you will get exactly the same. This is, I mean, the way to extend the system. Right. Okay, so we move a bit to the next topic about second. We're going to calculation. So actually, we learn a calculation technique from the Schrödinger approach. Now we're going to look into it again from the finite perspective. Follows that actually in the action. This is maybe example is that concept of a non-negative one-dimensional system. Okay? This is the part actually can be solved. Can be exactly so. Okay. What I mean by exactly so means that here, this type, this is one example, right? And then if you check, if you ignore this term, you're going to get a different. And in the homework, I'm going to put it in the harmony potential. And you're going to see actually that this can be so exactly, right? Okay, and then now I'm going to put the term like this. This is going to be a positive term. With this coefficient. For this kind of structure, you see in the context of Hamiltonian. In the Hamiltonian, you start with you have this Hamiltonian and below value. And you can do all things is previously a long time ago. And then here, what we're going to do with in the context of content. Okay. So, I say that there is always going to be S naught here. Right. And F5, later action. Awesome. Okay. And of course that you are complicated. Oh. Sorry about this. You can break your complicated into this way. And so, okay. Answer you later. Leave me alone. And so I have to follow this notification. Okay, I put this thing right here. Okay. Since is very small. Okay. Okay. It means that you can do the expansion of this one. So your polygon you take wall. Here. So okay, you have this kind of thing. Which is actually the first term. If you put all this into the bracket, you will get okay, this one, plus the second term, which is okay, this is your second term. And the first term, the third term, oh, I think I forget get QDI or mesh bar, that's sort of because we don't this.
Yeah.
Right. Right. This. Right. Okay. Okay.
Potential economics.
Oh, right. Thank you. Okay. This be careful with this because this fact it means that we need to integration like this. We need, this must be different in general. Because well, it's not necessarily this. Okay? All right, so let's have a look at this. So this one, the second thing. This is represent an interaction that can happen from the 0 to P. It's going to be happening between these two quantities. And suppose that the interaction takes place P equals S at X equals S. Okay? Okay. This means that this portion now can be divided into okay. So you use your integration into this way. So it's not really that not so well here we can separate here is the x naught to x t, right? Be careful with my x t. So I just split this integration into two bits, right? The first bit starts from x0 to x, right? And then interaction happens at this one, and xt, right? But the thing is that the position actually interaction taking place, it can be anywhere from -infinity to infinity. You know what I mean? But if you draw, suppose there's going to be it can be any of this. This is p equal to x1, and then this is x. I mean, I said actually, not infinity, but infinity. This is the position at time, but actually, it's actually interaction taking place. But we don't know which point, right, along this line, right, then we have to take into account all of it. You know what I mean? This is the reason why we have this kind of for this.
So x is a point on this side.
Yeah, x is the point on this side. And then that's the reason why we have to take all possible points on this side at t equal to s. Right. But we don't know. You have to take them all. Take them all. Then, so from this, your populator, I mean, your this whole expression can be now this is if you look at this is nothing but a propagator. Starting from x0, right? Oh, sorry. It should be x0 to x. Oh, I think I'm swapping around. It's here, and then it's here. Right. Sorry about this. S. Okay. So we have this. So if the pocket UK say which is actually going to be the first term, but which is I could take out, okay? Because this is we know how to solve this, right? Plus this thing, plus this thing, which is it's such a medium thing to write. Anyway. And this should be K of after all, right? See, this should be K of because it's not. Right. Okay. And which is this one. We are not going to look at this yet, but you can do the centric, then you can get, for this only one integration of this t, you have 1 point that you have you have 1 point here and you have to consider all possible, yeah, but here you have 2t, two times, actually. Alright. Then to be you have to split it into 2 parts. Right. That is the thing. Okay.
But split form is
yeah, it means that you're going to have another point, but that's right. That actually the second interaction taking place. Is that clear? And then you have to take it of the integration of the point that actually this time taking place. And then you can face more or less the same. Okay. Alright, so if you do that, finally you will get, believe me, but I'm not going to show you all the steps, and I'm going to leave you as a homework because it's not difficult actually. Trust me. It's the K2. I mean, it's this one. It is going to be S and F1, right? And cannot okay, you will have this thing. When the done with the splitting, okay, you see there is 2 points. Yeah, and you have 2 integrating. That's a big thing. And then you just add this thing into this line, and then this line. And then you can also consider version into integration. I mean, you can expand. Okay, let's see what we're going to draw a graph. This. So, the first term it's a straight line. This is representing the property. the first term, right? But the second term, you have TS here, right? And suppose this is a point actually, the internet taking place. You're going to have this, but it's not necessarily to be in this kind of graph. It can be any. I mean, you have a line along this point, right? This can, I mean, you can use, yeah. The point can be any on that line. You could, instead of this white graph, you could have this yellow graph. Okay? It depends on which point actually you're. But the thing is that we have to consider all the because we have this integration here at the front. This means that we have to consider all that the interaction will be taking place, right? This kind of thing. Okay? And then you plot with so you have this and that. This is the third term. So I put it in the form. The third term is going to be this one. Okay? And this is only the graph you could have. You could have graph like this, right? Graph like this. Okay, all possible way. Because you have this type of two integrations at the front. Okay? So, and you can think that actually there is a higher order in, you can do this type of thing. Right? I mean, I can draw a graph without computing thing. As from, that's 7 from. So I will have this from. Okay? In a higher order term, right? So, and then you go vertically to the right? So it's kind of up to you which order that you satisfy yourself. If you want to make things more accurate and accurate, then you have to keep going vertically forward and higher order extension. That's it. Is that clear? This is where we do the preservation in this technique. Right. I think, let me see. I think I'm going to stop here, and I think I'm going to give you homework to verify some mathematical set in the class and some further example. Like how to use this, how the technique to computing. It is very interesting. Any question? So next time, do we have a syllabus? I'm not sure after this. Yeah, after this topic or topic. Yes.
So the next is the technical teaching.
Oh, right. Okay.
But the Integron has a flow class in a multi-class.
So this is kind of okay. We can kind of adapt it and kind of adapt it to the situation that we have here because we have very unfortunate our class collide with the holiday. And I'm not going to let myself. Okay, it might not really clear at the moment. It's how to use this technique to compute perturbation as we did in the Schrodinger case. But in Schrodinger case, it's quite clear how to do that. But well, it should work in both ways. You should get the same visit. I'm going to give you homework and then you'll see. I might take some of the question from the previous homework with the technique that you start in Hamilton. And then you use this technique to compute all the technique. Let's see. You should get exactly the same. Otherwise, it's not the way that we want. Okay, any question on the K0? Yeah. K0 is the one that we know.
Yes. It is okay. It's not the same with any case, right? So in the example, it's free.
Yes. Yeah. Okay. That is a good question. So suppose that okay. So let's start with action. Yeah. I would mark here because so that we can show the classical action efficiency. You know that the second action is about the kinetic energy. Right. If you have only this term, you have three particles here, which is actually redundant. But if you add this, it's going to be the harmonic. And then this could be solved explicitly, and you're going to do it as a homework, right? And say that, okay, I might add something XQ, this kind of thing, that would affect my function. This is beyond the quadratic, right? Then you need this kind of technique in order to compute things. That is the reason why we need that. It's the same as they do with the Hamilton function.
Okay, so it has a different form.
Yeah, it has different form, but at the end, the goal is yeah.
Okay.
It's a different perspective. But very interesting because with only this, you could make actually this can be like a perspective. And then this is the one to solve. You could think that it's a perspective. You could do that. Because this kind of the three particle is kind of the first building block that we have in the hand. Right? And then everything that you add up into the overlapping units, you can think that that's the protector. But the thing that you add up into this market, even in the politics, it is still in the politics in the form, quantic form, you can still solve it explicitly. But if it's beyond that, you cannot, and then it needs this kind of technique. Okay? Okay, I think it's okay. Thank you very much. So, I think it's likely we're going to have activity with the last the whole day, board game. Then we need to find out thatเรารู้ว่าตอนที่สอบวันนั้นนะเนาะแล้วก็เช้าว่า
เพราะว่าเช้ามีเรียนการเรียน
วันไหนบ้าง
เอาจริงๆก็คือว่าถ้าเรียนการเรียนปุ๊บเนี่ย